Okay, we can get started. So we are happy to host today Vaastav Anand. He is from Max Planck Institute for Software Systems, co-advised by Antoine Kaufman and Deepak Garg. And his research is on improving cloud scale systems. Welcome to the University of Sydney, and we are very excited about your talk. The floor is yours. Thank you.
Thank you for the introduction. Hi, I'm Vaastav. As Shana's mentioned, I am from Max Planck Institute for Software Systems in beautiful village of Saarbrücken in Germany, where I'm part of the OS group. So today I will be talking to you about my most recent project called Blueprint, which allows you to generate variant implementations of microservice systems. So you traditionally, like large-scale cloud systems, have really been developed as monolithic applications. What that means is that all the functionality of the application is in one single process and is packaged as like one single binary or one single entity that is executed and is being hosted. And this is what a monolith really looks like, that every functionality is in that specific binary. However, in the last decade or so, we have moved from monoliths to microservices. What microservices really means is that you have now small, independent, loosely coupled services that are connected over the network, with each service performing a single capability. The reason for this move is because there are many advantages of actually developing your application as microservices. First, you can independently deploy any single component of your application. It's highly maintainable, especially if you think about a large-scale application when you have hundreds of teams. Trying to get them to contribute to a single binary would be very hard to manage. So this is actually something that works out very well for them. And it also allows something what we call language library framework heterogeneity, which really means that you can implement any component that you want in the best form with using the best tools available for that. So you can have parts of the application in C++, parts of the application in Java, parts of the application using a REST API, parts of the application using an RPC framework, totally dependent on what you're doing. But as you might imagine, that we've actually added a lot more complexity to the system now as compared to the monolithics, which means that there are a lot of disadvantages of using microservices as well, which lead to performance issues which are hard to diagnose, correctness problems that are hard to track, especially at geo-replicated scale, when you have services in one part of the world as well as the other part of the world, which can lead to service degradation and, in really, really bad cases, service outages, which has caused a lot of monetary damages and monetary issues for large companies at the very least. So I guess the question here is that are these disadvantages inherent, or can we do something about that? And the thing is that there are multiple ways that researchers at least think about improving microservices. First, by just changing components in the microservice application to improve performance. So an example would this be simply just replacing the RPC framework or communication framework. Of course, that would require a lot of work, but hypothetically, it's not something that should be too difficult to imagine as someone oh, I just want to use Thrift instead of gRPC or vice versa, right? The second is actually reproducing and analyzing bad end-to-end issues called emergent phenomena or emergent behaviors. And these are behaviors that are basically arise from complex interactions of simple components. And there are multiple examples of this in the literature as well as in the outage reports that you read. Popular examples would be metastability failures or cross-system inconsistency issues, retry storms, failure cascades. So nothing really good, but something that can really drastically impact the availability or the performance or even the correctness of the underlying system. So it's imperative that we actually, researchers, think about these problems and come up with solutions, right? And finally, prototype, develop, and evaluate improvements. This could be solutions to emergent phenomenon, just having new components to develop, or just new choices for existing components. For example, a new choice could simply be you have developed a new type of cache that is designed to handle large-scale workloads. Or if you have a new tracing framework that does something a bit more efficiently so that you can actually get access to the error cases very easily and you don't have to sift through a large volume of trace data or error data. So now that we have basically like talked about what are the ways you can actually improve microservices or combat some of the performance or some of the issues, I would posit that all of these improving tasks really require design space exploration. So if you imagine the microservice design space where each of these circles represents like a specific component and whether an application has that component or not, what I'm saying is that to actually perform any of these tasks, an application would have to be moved from one component to another. And that's what we call exploration. You have a question?
Sorry to interrupt you. Apparently, some people are looking for the Zoom link and
I can pause for the moment, so.
Sorry about the interruption.
No, of course.
I have actually one like just maybe.
Yes.
So you mentioned like cascade failure.
Yeah.
How is it specific to microservices as opposed to have everything on the same?
No, it's not specific to that. It's just an example of like how, for example, let's say if you have a failure in one of your services, that will propagate to like your other upstream service, that will keep propagating. And because of that, because you keep seeing more and more failures, eventually your application would just be bogged down because there are failures everywhere. So that's like an example of like how a failure in one of the smaller components, let's say in the leaf service, could actually propagate up and cause a cascade of failures. So it's not specific to microservices, it's rather a bit more prevalent, I would say.
And yeah, and also when we think of microservices, we think of like have them be like distributed, like
you can have them anywhere,
or even on the same machine.
It's so one of the beauties of microservice applications is that you can pretty much do anything you want to, right? Because technically there is no canonical representation of a microservice application, because by definition, it's like the definition is very, very loose. So as long as things are connected over the internet and are loosely coupled, it's essentially a microservice system. How you deploy them is actually a choice of like configuration of how you actually want to do things. And there are multiple ways that people actually deploy these applications, right? Some applications deploy all services or at least part of the services together, so that you minimize the amount of network bandwidth that is being used. And yeah, so you reduce the latency, you reduce the memory bandwidth and the network bandwidth. And so that's one of the design choices that you can technically make when deploying the system, is that we want all of these things. How do we actually put your microservice application in the deployment mode so that we can get all of these things? In certain scenarios, you're actually restricted by some of the goals of the microservice application as well. For example, let's say if you know you have customers that are going to use your application in different parts of the world, you have to have some kind of geo-replication for databases or caches, so that like you still see consistent data. I mean, that's not necessarily true that you always see consistent data in different parts of the world, but they try. So it's a bit of a
abstract kind of setting where like you make no assumption about where those things are.
No. So the whole point of our project is that you don't need to make those assumptions. And the whole point is that you actually specify what those assumptions are for your application, and that can dictate like what your design is. And we'll talk about it a little bit more, I think, in the next part. If it's not clear, we can always have like another question answer round thing.
Sana has been completed. I have one more question.
You can go on. I did.
Okay. Oh, okay, then continue.
No, please ask a question. It's supposed to be interactive, so.
But do you have a specific platform in mind, or is it pretty much everyone can implement microservices wherever they want?
Could you specify what do you mean by a platform in this scenario?
So I earlier used to experiment with something like Erlang, and because I also realized that this has been implemented in 2000 and back by Plan 9, this 9P protocol, and microservices can also be implemented using containers and so on and so forth.
Yeah.
So if you stick to a platform, then you can assume certain things for free. If you don't stick to a platform, then you can't assume.
So the way we try to be is we try to be as extensible as possible in when we actually generate the implementation. So you can specify, let's say, whether you want it to be deployed on as a Docker container, or you want it to be deployed in a Kubernetes pod or something, whatever it's called, or if you want these services living on like Amazon EC2 or something like that. So that's one aspect of it.
It's a heterogeneous system.
It's a heterogeneous system, right? And the second aspect is like, do we make any binding choices? A little bit. The language that we currently only support is Go. Go. simply because it's a little bit easier. We tried this with Python and it was not performant. But I think with Go, it was easier to deal with concurrency in the application itself and scale it up to like really high workloads. So that's one of the things, but it's not a theoretical limitation. It's more of a practical limitation in the sense that we only implemented our things for Go, but you can technically go and like implement bindings for different languages as well. So theoretically, you could have like a Java implementation of this or a C++ implementation, and we could support that. It's just that at the moment, it's.
So what's the protocol used between these services?
You can decide. It could be REST, HTTP REST. It could be gRPC. It could be Thrift. It could be something that you come up with your own. You can write a binding, like a compiler plugin that we have, and based on that, it should be able to support that. Because again, we want to make it as extensible as possible. So we can't make any assumptions about what might or might not happen. Yes. Right. Okay. I'll move on to the next thing. So let's imagine from the design space, you actually you have two RPC frameworks or communication frameworks, and you want to decide which one's better, right? So currently your application, let's say, is implemented in Thrift as opposed to gRPC, but you've heard from your friends or from the industry that gRPC tends to have better support for streaming services. So you want to be able to use gRPC. So an example of improving a microservice system using design space exploration would be you change the application from Thrift to gRPC. Now, of course, this would actually require a lot of work, but we'll get to that in a moment. Let's take a look at as to how existing systems are implemented. So existing microservice systems are simply point solutions in the design space of the microservices, which really means that they make binding choices about specific scenarios or specific components as to like, how are they deployed? How are they connected? Which RPC framework, or how are they communicating with each other? Which database they're using, which cache they're using. And these are things that like, you should be able to abstractly think about, be like, oh, I can just replace this. It's just hard work to actually go in and make those changes. So the issue with this is that with point solutions, exploration actually becomes hard. First is the reason is that design space is just too large. One specific implementation of an application cannot support all components, because you cannot at the same time have an application that is communicating in gRPC as well as communicating in Thrift, because it just feels, why would you do that? And I think that's one of the reasons why you cannot have any application be able to support everything in the world. So you need to be able to have multiple variants of the application with like things swapped out. The second is that modifying systems, let's say if you have an application, it requires a lot of effort and is time consuming. Changes can be cross-cutting across like different services or different components, as well as changes can be deep in the infrastructure as well, right? Like for example, changing, let's say, a cache or an app or a database is probably less painful than going and changing the RPC framework or the communication framework used by 1,000 services at the same time, because that would be months of work. And that's something that like we know as an example, because Facebook actually did do that with like in terms of moving from specific RPC frameworks to their implementation of the Thrift RPC framework. And they had to basically do it in steps and wave it off like over 2-3 months or something to even get like an RPC framework replaced. So to combat these issues and to make design space exploration easy, we present Blueprint, which is a toolchain for building reconfigurable microservice applications. And with Blueprint, we can generate system variants to explore the design space of microservices. Blueprint reduces the manual effort for exploring the design space, and it enables robust evaluation and experimentation. So you have to think about it in terms of like what a researcher would like to do, and not something that like, is this something that a practitioner or someone who's launching services at Twitter or something, well, not Twitter anymore, but at like Facebook can actually do, because that would be, there's a lot of like issues in terms of what it actually takes to get like a production level system and how it's over engineered to an extent to get like performance stuff. But let's focus on Blueprint for now. So how does Blueprint actually enable design space exploration? And we do it by enabling CBD. It has nothing to do with the CBD district of Sydney. I only found out that that existed after I came here. So
doesn't that mean something related to drugs also?
I also did not know that. It was pointed out to us by a reviewer as well. I was like, huh, if I had known that, I would not have picked this. But I think like one of my advisors at the time picked this name, and I was like, yeah, that makes sense. Let's go with configure, build, deploy, or CBD for building applications. You trust your advisor to a certain extent, and then you find out it's basically after cannabis, and yeah, you roll with it, I think. Pun intended, I suppose. So what does CBD stand for? So we basically have divided the microservice application development phase into 3 different phases. First one is configuring the system, which basically adds or replaces the necessary system components that your application should have. Then there's the build stage, which where the blueprint compiler builds the system implementation that matches the configuration. And then you can deploy the implemented system and observe whatever you wanted to observe, like do a performance measurement or reproduce a specific immersion phenomenon, or just test out if like a new component actually works correctly or not. And you can iteratively do it over and over again without requiring a lot of manual intervention. So let's say, how does Blueprint actually enable CBD, right? The first is to configure the system. It provides a set of abstractions that decomposes applications into multiple 3 orthogonal pieces. Then it basically provides a novel system representation. Okay, I think the mic that's my bad. So with the compiler IR, we actually have a system IR that represents the variant configuration that's provided. It's an intermediate representation that basically represents what the system should look like without actually instantiating the system yet. That's the job of the compiler. So the compiler would basically take the IR that it generated from the inputs, and then the compiler would generate a specific implementation. So the thing is that the IR here is a unique representation of the inputs provided by the user. And then you can just deploy the generated variant of the application and measure and do experiments like you're pleased to do. And you can iteratively do this over and over again.
So, okay.
Sorry. Yeah.
So why do you actually require this anyway? I mean, so I'm still not clear on the motivation part.
Yes.
Required.
So we go back to the 3 use cases that we wanted to support for researchers, right? So for example, the number one is changing a component, right? So you want to change a component to improve a microservice application. Doing that requires a lot of manual effort. Can we automate that? Number one. Number two, let's say there are issues that you see in large scale systems, right? For example, metastability failures. Can we actually easily reproduce them on test systems so that we can do some analysis or research and then use them for evaluation in our evaluation sections of the research papers we write. And then there's like prototyping new solutions, which let's say you have a novel algorithm for something, you want to implement it and test it out on a realistic system. How do you actually get access to those systems without being able to work with the companies directly or not? Let's say even if you have access to the system that is being deployed by like Facebook or something, they're not going to let you do all sorts of experiments on their deployed system because that would be a little bit bad for their business guarantees, right? So
in a sense, you want to be able to change the individual components fast.
Yes.
Okay.
For all the use cases the whole idea is that you want to be able to do that to do the design space exploration, which is what you need to actually improve microservice systems. Yes.
So is the idea of those autonomous pieces is if I want to change something instead of breaking everything, I just break whatever is in that autonomous piece, which is
and by breaking that, it would be like a 1-line change as opposed to like thousands of lines of change. So it's things like that. That's exactly the idea. Because we did like a survey of like things as well, and we found that people spend a lot of time changing things, which makes sense, right? Like any system that is sort of like functioning and alive, that will take a lot of time to change things in that. And I think we want to be able to quickly do it. Simply for researchers, I think this is more geared towards people who are doing researches and they need like example systems to test things on. So for example, if you're working on inconsistency or consistency issues in databases and geo-replicated settings, you need to have a system that actually showcases that issue. Otherwise, how would you even test out whether your solution is correct or not? To do that, you would have to like manually go and modify 1 or 2 systems to inject those issues and then be able to like run it with your application or run it with your algorithm to get there. So it's a little bit complicated and
but that means that you are asking them to buy into completely into your framework. That is, they have to develop their applications in your framework, right?
Yes, to a certain extent. The thing is, you can also have like certain pieces that are just completely black box. So for example, we use publicly available containers for a lot of the pieces. For example, let's say if you're using MongoDB or Redis or something, you just use the containers provided by those people and you can just directly connect to them. You don't need to have those be part of the application itself.
Right, but those things that you want to manage, it has to be part of the application.
Yes, that is true. But the thing is that this is exactly one of the drawbacks of like why a production system at a big company might not want to do this. Because then it gives that like central point of failure that they didn't want in the first place, right? So I think this is where like it comes down to that this is more geared towards people who are actually researchers and doing research instead.
Have you looked at these things in the operating system space where they have distributed operating systems? What you described sounds very close to distributed operating systems, like Amoeba. Or where you can actually write in any language, but you have to compile into the internal code, and then you can essentially push it over to any system that you want. And the whole thing works as a single OS.
So I think one of the things that I did look into was more along the lines of Flux OS Kit. That's also a bit of an
yeah,
right? Yeah, I think it's from like late 90s or something. So that one was it's essentially a bit like that. Their whole point was like you just need to write glue code. Here what we're saying is that you just
Flux OS Kit was more about building individual single
and then connecting them using writing just the glue code, because you can develop individual components and then write the glue code, and that's all you need to do when building systems or building an operating system where you want to use multiple pieces from different places. So it's a bit more like that, in my opinion, rather than Amoeba, where like here if you have components, right, you have individual independent components and you want to connect them, then all you need to usually do is like write infrastructure code. What that means is that, for example, let's say if you wanted to use gRPC, you would basically write the gRPC bindings for your service. That does not change the internal application structure at all. So for example, let's say if it's a social network application and you have a functionality for composing a post or uploading a post or something, that's not going to change whether you use gRPC or Thrift. The infrastructure in front of it will change most likely. So that's where we are saying that all of that changes are the things we want to be able to make reusable. Because why would people write that thing over and over again for different applications and different services when it's something that easily can be automated? Does that help? Okay. Any other questions before I move on? Okay, sounds good. So what does the blueprint toolchain looks like? So we have, as an input, the user provides what we call a workflow specification and a wiring specification, which is combined together to generate the intermediate representation, the unique intermediate representation for that variant, where the compiler will use that to generate the system that can then be deployed on whatever platform was selected for deployment by the users itself. So let's take a look into like more detail as to what these individual pieces are. So let's start with the input first, because that's what the users will have to provide. So the first thing is that we actually the inputs are divided into 3 pieces. The first is the workflow logic, which is the workflow specification, and it represents the application level logic and end-to-end flow of executions. So you can imagine this more in the lines of what does a system do at a high level? For example, if it's a social network system or a reservation system or a food delivery system. The second piece is the scaffolding, which is the wiring specification, which is part of the wiring specification, which specifies what backends to use, what frameworks to use, or which libraries to use that orchestrate execution. It's completely opaque to the workflow because It can also add features such as tracing, replication, timeouts, retries. All of these things don't really actually impact the workflow specification at all. That thing is completely independent of this. And finally, we have choices. So these are choices of specific implementations of components, like which cache to use, which database to use, which communication framework to use. And finally, the choice of deployment, which basically means whether you want this to be in a Kubernetes cluster or normal Docker containers or Amazon, wherever you want your system to be deployed. So let's start with the workflow logic. What does that actually look like? So this is an example of what one service looks like. In like our workflow specification, you can see the first thing is that it contains the service declarations and definitions. So what this actually provides, this interface tells you that there is this thing called a compose post service, which exports one single API called compose post. And then there's an implementation of that service, which is the compose post impl that takes two dependencies, post storage service and user service, which are passed as parameters to the constructor of that specific service. So it's a bit like dependency injection, where like at the workflow level, you're not actually instantiating anything. Things will just get passed into it, and that allows us to like do a bit of modifications, which we'll get to that later. And finally, with the dependencies, each function can actually be implemented in just a few lines, because you don't have to worry about how things are implemented. You just need to worry about what this service actually should do at the heart. So here you can see there is no code about launching a server. There is no code about launching like serialization of arguments, deserialization of arguments, or return values, or any other features that you might want to do. There's no mention of tracing, replication, retries, timeouts, anything, because the workflow specification does not have that. That actually comes in the next part, which is the wiring specification. So in the wiring specification, we actually make declarations of instances. Let me say, like, here is line number 9 is the declaration of the user service, which takes like a user database that was defined in like declared in line 8. So it's basically like building up your application line by line and adding features. So you can add features like RPC server. You can actually have a gRPC server attached to a specific service, and then you can actually group these things together as well in containers or in processes or in specific regions or domains, depending on how you actually want to structure your application. So in the wiring spec, you actually do the declaration, define the topology of the application as to which services connect with the others, instantiate components, and select features that you need to apply. So using that, now we actually will look at what actually happens and what the compiler does with these pieces, 3 pieces of input. So the first thing you actually do is you actually have compiler plugins. Wait, no, that's the wrong slide. Sorry about that. First thing you actually do is you actually build the intermediate representation. So for the wiring spec I just showed you, this is the intermediate graph representation that is built by the compiler. Don't worry, this is a very horrible looking diagram. So we'll not focus a lot into this, and we'll figure out what is actually in the IR itself. So first is the component nodes. What does a component mean? They're entities that will ultimately be instantiated in the deployed system. So these are the service instances defined in the workflow, or backends and choices like databases. Components can exist at various granularities, and there's a one-to-one mapping to instances defined in the wiring specification. So if you declared an instance in the wiring spec, this will come up and show up as a component node in the IR. As I mentioned, you can actually have them at different granularities, and you can merge things together or group things together. So you can have a service level granularity where a service is just an independent entity, or you can have a process like an operating system process that is actually catering like 2 different services. Or you can have a full container where you have one service and like maybe a sidecar service in that as well. Or you can have a full region, which is just built of like multiple services and multiple replicas. So you can group things in any way you want to, or group instances in any granularity you want to. And this is done using the namespacing nodes. Then there are the dependency edges. So what is actually an edge? Well, remember that like services actually need to communicate with each other, right? So the edge really represents a communication link between 2 components. And that's what we call a dependency between 2 components. If 2 components are connected in the wiring specification, then there is a dependency edge in the IR as well. So there is, for each edge, there's a visibility check. So for example, if you encode some components together in the wiring spec, you have to make sure that in the instantiated system, you can connect to them in real life. So you can actually have a situation where, let's say if you have an edge between service A and service B, but if service B is not exporting anything over the network, how will you actually ever reach it? So in that case, the edge will have zero visibility. So this is usually an error, but some people like to do that in the microservice applications infrastructure. So we had to support something like that. But the whole idea is that you want to be able to connect things. And if it does not connect, then edge is not visible. And that's probably a bug, but it is what it is. And then on top of that, we actually have something called modifier nodes, which actually adds scaffolding to components. This is where you dictate, you specify how things are going to be done. And you basically specify what orchestration is going to happen, as in like whether you want tracing, timeouts, retries, which framework you're going to use. And the way it works is that if you imagine the red thing is service A and the blue thing is service B, you'll basically inject class nodes or something where you basically wrap around the service call. Let's say if you're calling service B foo or something, the blue service foo function, it'll make sure to inject all these things in between. So there will be a retry, there will be timeouts, there will be a network client, like a gRPC client, and then it will go over the network. And on the network side, on the service side, you'll be doing the serialization and deserialization, you'll do the timeouts and stuff, retries and everything, and eventually you'll reach the workflow specific definition. That might be a little bit too much to take together, so we'll walk through this over in step by step. So first, to tell you how we actually generate the system from IR, we're going to talk about compiler plugins. The compiler plugin basically adds concrete behavior to the compiler to operate on the intermediate representation. It can perform the following operations. It can modify a node, it can add a new node, delete a new node, and all the scaffolding and instantiations are essentially implemented as compiler plugins. For example, it specifies how to generate code for a given component. So now that we know, let's take a look as to how the generation works. So we have a hierarchical generation where we actually do the generation in reverse topological order in the IR graph. The reason for this is that it actually makes sense because you're generating things in an order where all the dependencies are generated first. All your dependencies are generated first before you are generated or your service is generated. That makes it easy for us to generate systems. So let's take an example. So we have a compose post service, which was declared in the wiring spec. We have a couple of modifiers, one tracing and one network one, and we have put them into two different namespaces. The one is a Golang process namespace, and the other is a Docker container namespace. So the first thing that will happen is that you actually start at the service definition because it's the leaf node in the thing, because that one has like no other dependencies, right? So you start from that, and internal logic of anything is actually left unmodified. So anything that is provided in the workflow specification is used as is. This guarantees that whatever the user wrote as input is preserved, and whatever they think should be executed in the application will be executed, because we do not want to modify anything the user provides as input. Next thing what will happen is that you actually basically wrap around that specific whatever API that was exporting and put tracing in front. So now this thing, in this scenario, the tracing is provided by the Zipkin node, or so you have Zipkin as your tracing framework. So what you do is that in this scenario, the compiler will only interpose between the calls and connections between components and not modify the internal node itself. So the Zipkin node that is generated by the plugin, the Zipkin plugin, is a standalone entity that just fits in between the two service components. And we keep on modifying this over and over again, and we basically end up with like a gRPC modifier next. So now, if you imagine you have service, the internal service, and then you have tracing in front of it, and then you have the gRPC. So now you have actually given it some kind of a connection, a network connection, so or some kind of a server that you can use, that can be used by potential clients to connect to the service. So the next thing after that would be you generate the Go process, and now you finally generate the Docker container, which is essentially the thing that you are going to run. So you can run a Golang process as well, but Docker containers are usually easier to run and distribute and reproduce. So it's one of the things we actually support inherently, where you can just have your service or have multiple services as the Docker service. as a Docker container, which can then be generated. So this proceeds for pretty much the client-side instantiations as well. I was showing you how it was happening on the server side, but on the client side as well, depending on the components or the features that you have selected or the scaffolding you have selected, you will generate the same way. In addition to that, there is another thing called, another thing that happens is that resolving the ports and addresses for service discovery. Because you need to be able to get like a proper address to connect to a service, right? So that's something that the compiler takes care of. It uses sensible default values if they're not provided by the user, but we prefer that if you provide the values, it's better, because then you won't be any unexpected issues and you know what service is running where. You can run it on like multiple different machines or single machine. It's completely up to you as the user. So now that we have that, we can generate the system, and we'll generate the whole source code of the system, as well as the deployment files. So like all the configurations, let's say for Kubernetes or something. And you can use that to either run it directly or modify it to like, add some more things that you want to like specialize it because you want to use it as is, or you can just run it as run the variant that we generated to do things as you would like to. And you can obviously like keep on doing this over and over again because it's a simple compiler and you can recompile things as many times as you want. So all of the implementation is actually done in 10,000 lines of code. The core compiler abstractions are in 4,000 lines of Go code, whereas we have a wiring specification, domain-specific language, a DSL, in like around 800 lines of code. Right now, we only support Go. Does not mean that we can't support other languages. It's just I'm the only person who is actually doing any kind of implementation, so have mercy, is what I'll say. So now that we have the implementation, let's see what we can actually do with this. So the first question we ask is, do Blueprint's abstractions reduce programmer effort? Second, can Blueprint help elicit emergent phenomenon in microservices? Finally, third, can Blueprint help prototype solutions and improvements? And is Blueprint extensible? So let's start with whether the Blueprint's abstractions actually help reduce programmer effort. So to do this, we actually started with like 5 publicly available microservice systems that are widely used in research literature as like deployment targets or evaluation targets. What you're seeing is the lines of code required that someone had to manually write to implement the system. Now I'll show you the amount of lines that we had to write to reproduce that system, the specific implementation of that system. And you can see we can get up to like 5 to 7x reduction in terms of the manual code you need to write. But that's not all. You can actually do this over and over. You can do reconfiguration of stuff over and over again. And compiling only takes like a couple of seconds in the case of like services where there's like 60 services or 70 services. You can scale it up as well. So we tried doing this, and it's not reported here, but we tried doing this for like an application that has 2,000 services or 2,400 services based on a trace data set provided by the Alibaba folks. And compiling that from a trace data set was around 10 minutes. So you can get like large systems within 10 minutes, and I think.
What's the average number of microservices used by applications? Like, do they have a sense?
There's no one answer to that. It really depends on the scale of the system. So at the big companies, it's very high.
Like what is very high? Like 10,000, 100,000? No,
not 100,000. It's in the thousands. It's definitely in the thousands. So I think if I remember correctly, Uber is 5,000 services. Meta is a little bit different. I think there's a nice paper from Meta at Usenix ATC conference that talks a lot about like how is their microservice infrastructure built and like what is the fan out, fan in, and it's the same with like Alibaba as well. So they had 2,400 services that were not database or cache instances, and then on top of that they have stuff. So around anything greater than 1,000 is like high scale. Usually mid-sized companies have it like around 9,600, maybe a couple hundred, but not more than that. And then there are smaller applications which are like 20, 30 services. But in that scenario, it's not really clear if you're actually getting any advantage of using a microservice application and whether it should be a monolith or not. But that's a question that the community has been dealing with and trying to figure out. So, yeah. So we can easily recompile things together. So let me give you an example of how we can actually reduce exploration effort. So let's say if you want to change software design choices for exploring the performance or improving the performance. Let's say our implementation is built with gRPC. Next we can do is like put thrift as well. And we use like, after that, we can change the client post size for like how many clients you have at the same time for in front of each service. And you can change that. In this scenario, it really doesn't help. But like the other thing you can do is just change it from microservices to monolithic. What that really means in this scenario is that you take all the services, you combine them and compile them into a single process that can just be launched. In this specific scenario, because the number of services are so few, you can actually get a lot of performance boost by going to a monolithic service instead of a microservice application. Yes.
I've got a very dumb question.
Yes.
How do I read this? Why does it come back?
Oh, so these are the throughput latency graphs. So at some point, you're going to basically maximize, like reach the maximum throughput you can get, and you cannot go further than that. At that point, if you keep on increasing the workload, right, your latency will increase, but your throughput will not. So your throughput is basically plateaued.
Okay, so exactly both of them are as a function of the workload.
Yes, yes. So the latency, you start with like you start with 3,000 requests or 1,000 requests per second, your latency is very low because it's easy to quickly do things, right? And you're not overloaded. But if you keep on increasing, eventually you'll get more throughput, but your latency will suffer as well, obviously. And at some point you'll be like, you cannot scale past a specific amount. And to do all this, you actually need to change only fewer than 10 lines of code in the variant specification. Actually, for changing the RPC framework and client pool size, it was like 1 line of change. Changing the architecture, that required like 9 lines of changes.
But I mean, even after hearing that, I can't read the graph.
Yeah.
So you're increasing the average good put.
No, so that's the measured. So x-axis is the measured good put.
Measured throughput.
Measured through good put, not errors. We're not counting errors in this scenario.
Okay.
So what you're doing is, let me describe an experiment a little bit in more detail. So what we do is
you're not increasing the x-axis. There's
No.
nothing else that is being added.
No, the workload is increased as the x-axis. So let me.
It's not shown here, right? That's what is confusing, I think.
It is, but it's kind of hidden. Let me explain it. That's why I'm saying let me explain it for a moment. So what we're doing is we're basically doing a workload of like, let's say 1,000 requests per second, 2,000, 3,000, 4,000, up to like 50,000 or whatever, right? But when let's say, even if the workload is launching that many requests, when we measure what the throughput is on the system side, if it's like 50,000, we're not seeing 50,000 in the case of like the blue line. It will plateau at like 30,000 because that's the maximum throughput it can reach. So even if you increase the workload there, you can fire more requests at it. You will not get any good numbers from it. Does that make sense? Okay. Right. So we can reduce exploration effort. Now the question is, can we actually help elicit emergent phenomena in microservices? So to do this, we basically generated 2 variants of available systems, Death Bench Holder Reservation and Death Bench Social Network, and we generated different variants of these systems and deployed these variants for different workloads. We show 2 different phenomena, metastability failures and cross-system inconsistency. Yes, so according to the literature, there are 4 types of metastability failures. So this is a paper from OSDI 2022, which talks about how they occur in like real systems. So there are 4 types, where we have one, which is the load spike trigger. So you'll have a sudden increase in the load. That's one trigger. And the other one is your capacity to deal with workload is just reduced. And then on top of that, you can have, because of these triggers, you can either amplify the workload, or you can actually fall the capacity degradation. It just keeps reducing and reducing. So in the real systems, we actually do not have any of these metastability failures. In the systems that originally were implemented, none of these exist because they don't have the components required to do it. So adding those components took us around only 4 lines of changes. And with that, we can basically showcase that we can have emergent phenomenon or metastability failures in microservice systems. So a typical thing about a metastability failure is that if you actually go over time, the latency will basically keep spiked. And even after you have removed the trigger, which is the red bar, it will never recover. Your system will be in a degraded state until and unless you completely shut down your system and start from scratch, or like do workload sharing to an extent where 90% of the workload is just not happening or is not being serviced. So in this scenario, you can see that we basically reached the failure state or metastable failure state in all of these situations, based on the different types, and it required only 4 lines of code changes to do that. The second one is actually reproducing cross-system inconsistencies. So what that means is that if you have a read followed by a write, it does not match the written value. So let's say if you wrote x equals to 5 and you got a success message from the application and everything was working correctly, and if you do a following read, it will not read as x equal to 5. It will read that as an old value or something. This only happens in replicated caches or replicated databases, because if you have replicated versions, it takes time to apply a specific change to a specific application in replicas. And then it is more popular, or it's more apparent when you have the replicated instances are geographically distributed, because you can imagine that if you have your primary in the United States and your secondary in somewhere in Japan or let's say Australia, that would take a long time for the primary to get the value from the secondary. In that scenario, obviously, your client has to make the request as well for that specific value, and has to know that the value it was written that was a success is actually not the same that you're reading it. So it's a little bit more complicated, but there's a paper at this year's SOSP as well called Antipod that deals with these specific inconsistencies, and has been mentioned in different parts of different papers before as well. So it's impossible if do not replicate it, and we only needed to change 2 lines in the while specification to actually add replication to the system. So as you can see, in the non-replicated case, we do not see a single inconsistency because you cannot really have one. But in the replicated case, we actually see a very small amount of inconsistencies because our things were located very close to each other. So we only see 0.1% or 0.2%. However, let's say if we actually increased the distance and the time it would take to for the primary to communicate to the secondary to apply a specific change, we could increase the number of inconsistencies. But the whole point is that with minimal changes, we can actually showcase this specific phenomenon as well.
That increases because, so when you increase the wait time beyond 900, the inconsistency increases because something's timeout, or?
Inconsistency should probably go to 0, because wait time is how much time you're going to wait before you actually do a read request. So you're giving it time to be able to apply the change. Yeah.
So why does it increase at the end? That's what.
So the thing is, this was done with a few number of things. So it's not very robust in terms of the numbers that we're showing here. The whole point is that we don't really know how much time we should wait before it gets applied, because there are a lot of conditions that dictate. So we have to make sure that we don't really know what the number is before we can actually say that this is reached to 0. The whole idea is that eventually it will reach to 0. We don't know the number in advance because that's just hard to know. And it's totally dependent on the operating conditions.
So it's a statistical artifact.
Yeah, pretty much. Yeah. As long as it's going down and as long as it's more than 0 for smaller wait times, it means that we have been able to see or perceive cross-system inconsistencies. So next question is, can actually Blueprint help prototype solutions? And we take one of the metastability failures, and I'll tell you how this metastability failure actually manifests. So first, there's an increased load, which leads to more request timeouts. And because there are more timeouts, there will be more retries in the function or in the application. Now imagine if you have services that are always retrying when there's a timeout, you're going to keep on increasing the load over and over again. That means that your performance will eventually stay degraded, even if you actually remove the increased workload, right? If it's gone back to normal, you still have all of the old stuff that is multiplying over and over again. So question is, what would be a potential solution? Not saying this would work, but for all cases, but like a potential solution would be circuit breakers, where after a few tries, you basically stop doing any kind of work and you basically stop any of the new requests from traveling through, and you basically break the circuit, which allows the system to actually eventually heal, even in the presence of increased load. So it did multiply, but here the circuit breaker kicks in, it reduces the value, and then it kicks in again, and then it allows the system to heal and like go back to normal. So this is something that only required like 3 lines of code changes in the wiring specification of the system we were using. So you can see that if you have a specific solution, you can integrate it with our compiler and then apply it to any different applications or any number of applications you want. Finally, what we also did was actually reproducing results from research. So we took like something called Sifter, which is a tracing framework or tracing sampling framework. And what they did was that they actually modified the application, which took like 2 to 3 weeks according to the Git commit history and 1,300 lines of code changes to get to the point where they can have the system ready for like their specific solution. So to integrate their solution Sifter, it took this much and like this much time and effort to do it for one specific system. We did the same thing and it required only 3 lines of code changes. And you can see that the structure of the graph is the same as the one on the top. The numbers are different because, well, it doesn't matter what things were being used or what false cases were being used or error cases, as long as you're inducing anomalies. The whole point of the system was you want to keep the anomalous traces for further review. So they injected 5 anomalous traces here, and we injected 5 as well. It's just that ours were a little bit more anomalous because they were still generated by the system. I think that was the one here with like more manually configured, or was a configuration issue, so different. But anyways, the point here is that what they accomplished in multiple weeks of work with a lot of changes, we did that in like 1 day. Maybe I remember doing this in an afternoon with like 3 lines of code changes. So the last question we ask is actually Blueprint extensible? How much time or how much effort does it take to add new features or new components to it? So first is like adding new components. So we have like these components called what is a cache, which took like only 12 lines of code to add, tracer, which took like 45 lines, NoSQL DB, which is like 27 lines. So it's very few amount of lines that you actually need. Is there a question or?
It's like a computer.
Okay, no worries. That's all right. And then we can actually add new choices as well for these components. So for example, supporting Redis and Memcached only around like 200 lines of code for our system, and then you can just completely use it. Same goes for like adding a lot of tracing stuff. I'm not showing you all the features and all the choices because we support a lot. I know it's hard to fit in one slide. But the whole point is you can do it in like a couple of 100 lines of code, and that's it. And you can add more features as well. So like you can add retries, you can add tracing, you can add like replication, you can add some client pools, or you can add some other things as well. And usually takes a few hundred lines of code, and it's a one-time cost that is actually amortized over time as well, because you keep on reusing these features on multiple applications as well. So you're only paying this cost once. It's harder to actually implement something that would be used in the compiler, obviously, but the thing is it's amortized over time. So eventually we provide, basically in concluding, Blueprint provides a toolchain to reconfigure, rebuild, and deploy microservice applications. It can generate variant implementations of an application to elicit phenomena or explore the design space of microservices. It's accepted at SRSP 2023 and it's publicly available. So please feel free to use it if you want to. If not, then that's all right too. Yeah. Thank you. I think that's all I have.
Did that yesterday, so I'm not sure if it's working or not. I do wonder about your choice of where to change. So, for example, developers are really loath to change their language, but they are happy to change their resources or what database they use and other things. But if you ask them to change from say Java to let's say C#, they are not going to do it. So here you are saying that you need them to buy into say Go or one of the languages that you support. So
I agree with that to an extent. The thing here is that what we're saying is that this is not something for developers of like real applications that are going to be produced. It's more for researchers who just want something to be able to test their things on. Okay, so the use case there is like a little bit different, which means the requirements actually change a little bit as well. Right. Of course, you can actually, let's say if this was like a proper industry product, let's say you could technically support multiple languages as well. So you could provide the input in different languages, and you can have the generated variants in different languages as well. There's nothing fundamentally limiting about our approach. It's just that the current thing that we have built only supports one.
Question online from Alan.
Yeah.
Alan, would you like to?
Thanks very much. So my question is sort of at a higher level. Could you point to sort of a place where you tried something and it didn't work at first and you had to do things differently? Because I mean, what I got from this was sort of the solution, but which has some very, very nice technical stuff, but I didn't really see where the intellectual sort of sticking point was. So can you perhaps point to a place where you went down a wrong path and had to backtrack?
So went down a wrong path in our implementation of this, or went down the wrong path in the motivation? I'm not sure if I'm
in designing and building all of Blueprint.
So like there were multiple places where we picked the wrong choices. So designing the workflow specification, designing the wiring specification, and basically like separating them out was super hard in terms of like, how do we actually even separate these things out? We can think about it in terms of like, intellectually these feel different, but then there are things that we think that, oh, like for example, a load balancer, where does that belong? Does that belong in like the application workflow specification or something in the wiring spec? You can see that there are multiple ways you can implement this. So our approach to this was that because there are multiple ways of doing something, we should not be limiting ourselves. So initially we had limited ourselves with, oh, this can only be done here and that can only be done there. But we realized that that was actually not the right solution or right approach to this, because we wanted to be able to do whatever an application developer would want to do. I think that was basically like one of the situations where we ran into in terms of like trying to figure out what's the right thing. And then the other obvious part is like the design of the intermediate representation itself, because we want to develop something that's easily used in terms of generating the application or generating the final implementation of the system. So our first couple of tries were very ad hoc, implementations, and they did not end up passing muster, right? Because they were just ad hoc and there was no design to it, or it was very poorly. So we had to come up with the right.
I'm very sorry to interrupt. We have another seminar starting soon, so we'll have to wrap up. Thank you everyone for joining. And Alan, maybe Vaastav can email you, or I will make sure you're in touch so that we can exchange contact. Thank you very much.
Thank you so much for having me.